Okay, so we're going to be talking about capacitors in series and parallel. So we're going to be deriving equations for the total capacitance in series and parallel using energy conservation and charge conservation. You can also say the Kirchhoff's voltage law and current law. So we're going to be applying those. Okay, so let's start. So we've got here two capacitors in parallel. So let's first use the energy conservation. Okay, so energy conservation. Okay, so if you remember from your AS level, the potential difference across this capacitor will be V1, the potential difference across capacitor C2 will be V2. Okay, and the EMF of the battery, or the total voltage, will be equals to V1, and V1 will be equals to V2. Okay, if you remember this, when things are parallel, the potential difference across is the same. Okay, so that's the first thing. Now let's look at the second one, which is going to be charge conservation. Okay, so this is kind of similar to the current. So what's going to happen is that the current will split and then it will join together. So basically the charge will split between both of these capacitors, just how the current used to split, and then it used to we used to say the current incoming is equal to the current outcoming. So that's the same thing here kind of as well, where we have the charge being split. Okay, we're not talking about current here, but just to connect it so that you get the rationale behind it. But yeah, but the charge is being split between both of these capacitors. So we've got the total charge is equals to Q1 plus Q2. Okay, so we've got these two equations here, and we know the charge is equals to the capacitance times the voltage. Now we're going to kind of link both of these equations up. So I'm going to, instead of the total charge, I'm going to write C total, V total is equals to C1, V1 plus C2, V2. And V total, V1 and V2 are the same, so they're going to cancel out. So C total is equals to C1 plus C2. Okay, so that's the first thing. Now, we can also write this in a more general way, where we can say the C total is equals to the sum of the capacitors of n number. Okay, so n number of capacitors, we're going to sum them up, and we're going to get the capacitance of them. Okay, so that's basically the equation right over here. Right, there's just a bit more of a general way to write it. What if you have like 7-8 capacitors? So n is going to be equals to 8. So that's kind of what we're doing here. Now let's talk about series. So when capacitors are in series. Now here again we're going to apply the energy conservation first. Energy conservation. Now if you remember again, here the voltage will be split between C1 and C2, and yeah, so it's similar to what you did in AS level, we're just connecting things here. So again, V total is equals to V1 plus V2. Now, second, we're going to talk about the charge conservation. Charge conservation. Okay, again, we can think of this in the AS level mindset, where we talked about the current being same. So the charge is going to be the same as well throughout. So we can say the total charge, okay, is going to be equals to Q1, and Q1 is equals to Q2, where Q1 is the charge on capacitor C1, and Q2 is the charge on capacitor C2. Okay, so I hope that's kind of clear as well. Now again, we link these two equations that we have, and we're going to get our charge, we know, is equals to C times V. Okay, very important. And V is equals to Q divided by C. Okay. So we're going to use this equation. So V total is equals to V1 plus V2. So we can write Q total over C total is equals to Q1 over C1 plus Q2 over C2. Now, all of these Q's are the same, so they cancel each other out. So we're going to end up with C total, 1 over C total is equals to 1 over C1 plus 1 over C2. Now you're going to inverse both sides. So we're going to get C total is equals to 1 over C1 plus 1 over, this should be 2, 1 over C2 minus 1. Okay, so that's going to be this. So we have proved the equation for the total capacitance in series as well. Okay, just one more point. Let's discuss that as well. Then we're going to do one question. Okay, so it says add a capacitor in series and the equivalent capacitance decreases. Add a capacitor in parallel and the equivalent capacitance is going to increase. Okay, so basically this is the same way we thought of resistance in parallel and series, but with the resistance in parallel and series, if you remember, let me just write that down. So when we had resistance in parallel and then resistance in series. Okay, if you remember, if we add resistors in parallel to each other, the effective resistance would decrease. But if you add them in series, the effective resistance would increase. That's the same idea here, but it's kind of flipped around. So in capacitor in series, if you see here, the equivalent capacitance decreases. And if you have it in parallel, the capacitance is going to increase. So basically the ability to store charge in series is going to be less than in parallel. Let's try this question out. Okay, you can read the question. Basically, we've got a circuit where the capacitor can be charged and discharged. It says the student connected a second identical capacitor in series with the first capacitor. She connected the switch to position X to charge both capacitors. Explain how the magnitude of charge stored on each capacitor compares with the charge that was stored on the single capacitor. Okay, so we've got the same thing, but we've got, I'm not drawing the rest of the circuit, just going to show the two capacitors in series. Okay, so what's going to happen here is 8 volts is going to be split 4 volts here, 4 volts here, and it's going to be split equally. So this is going to get half, this is going to get half, because both the capacitors are identical here. And on the other hand here, the capacitor is going to get all of the 8 volts, right? So we're going to take this capacitor over here and compare it with this capacitor over here. We're going to be comparing their charges, okay? So we know Q is equals to CV, okay? And here if we see the potential difference across this capacitor is more, so the charge is going to be greater. So charge here is going to be more. I'm going to take this capacitor here, Q is equal to CV. We can see that the potential difference is less, so the charge will be less when compared to the capacitor alone. Okay, so basically your answer will be that the potential difference divides among the two capacitors when in series. Okay, and then you can write the charge stored on each capacitor is less than the charge on the single capacitor. Okay, that's going to be your answer.